Welcome to the Private AI Lab, the podcast where we experiment, explore, and debate the future of AI behind the firewall. I'm your host, Johan, and every month I have a guest in the lab to break down real-world use cases, challenges, and innovations shaping private AI. In this episode, Frank Denneman from Broadcom returns to have a chat about the AI resource management solutions he has been working on, including 2 free-to-use sizing tools on his website. Enjoy the episode. Welcome back to the show, Frank. Really, truly feels good to welcome you back as the first returning guest of the Private AI Lab. How have you been?
Good, and I'm honored to be the first recurring guest, of course.
Awesome. So the topic of today's show is, the stuff that you've been working on with your team for the last couple of months, everything that's new in resource management, and some of the tools you've been you've been building. And in the previous episode, I asked you to introduce yourself. Well, hopefully the world knows now who Frank Denneman is. But I do have another topic to kind of dive into before we dive into today's theme, and that's like there's a Spark on my desk, and you bought one recently as well.
Yeah. It took me a while to pull the trigger. But when I saw your video with you and Luke on GTC, I'm like, yeah, let's get this thing and let's start to understand what's the capability of primarily OpenClaw and of course now with NVIDIA's NemoClaw the element. I thought that was a good idea to basically dive into that. So I've been digging into that, been understanding the structures, how to deal with it, how to work. How to get it working, right? That's an interesting. It was an interesting journey. It sits over there. I cannot reach it,
No.
but it's always on, and it's a very interesting concept to be sure.
So what are because there's, and I'll leave a link to the show notes, obviously. But you wrote a multi post journey of how to boot up the Spark, how to deploy NemoClaw, how to configure it. So what are, to listeners who might not have heard about NemoClaw yet, could you kind of briefly explain what NemoClaw is?
Yeah, the way I see it is NemoClaw is a secure wrapper around OpenClaw. OpenClaw allows you to run agents to do long-lasting processes to do whatever you want it to do. You can basically start with the trivial things, which I won't do, is managing your email, because I don't believe in that. But too scary. But research agents, all of that stuff, which is very interesting. Just give it a topic and let it search for a long time on targets you want to focus on. So one of the things that I'm looking into right now is, can I extract information from like a Slack channel? So if you look at MLOps community, it's a very, very healthy community that's been going for a long time. They have a tremendous amount of information that is very interesting to understand. Can I use a research agent that basically just looks at the Slack channel and then give me an overview of what's interesting for me? So I'll give some keywords. So that's the stuff that I'm looking into right now. But getting back to NemoClaw, it just runs that OpenClaw environment in a sandbox, and it allows you to provide some security measures, like you can see it as a firewall type of approach, where you basically say you can only go to this address outside of the box with this tool. So you have to be very specific what it can do instead of just blanket statement, do whatever you like, right? The other interesting thing is the durable state, meaning it will save conversations, it will save the history on your disk. So it will append everything that it learned to those files that you save. And every time when you do something, it will basically analyze those files, those history files, to understand, okay, what's my purpose? What is my persona that I need to provide? Meaning the persona, meaning you or me, right? And
Yeah.
that's an interesting place. So that's what you hear a lot of people say. Yeah, he really understands what I want. Yes, because it constantly adopts its history. Basically, it's KV cache, if you would say it like that.
Yeah, and one really interesting aspect of it is like so. Obviously, in the last couple of months, we heard a lot about OpenClaw and also kind of the cases where someone gave OpenClaw all permissions it needed. Like, you go manage my life. And I heard a case where someone texted OpenClaw and asked, like, okay, so I'm out of milk. Could you arrange some milk? And like a day later, there was a truck with not just one carton of milk, but like a dozen. Something went a little bit wrong. Or also the cases where someone gave OpenClaw like a prepaid credit card to start, run some cryptocurrency trades,
Okay.
where at first you saw like a trade increase, but all of a sudden like everything was gone. So it's but also like things like crypto tokens being shared, and so this is where kind of NemoClaw comes in, where we
Yeah.
indeed can secure stuff. But and something you mentioned is really interesting because of the human context, or the context that NemoClaw learns about you as a person. I saw that Claude now from Anthropic now also has some kind of agentic capability with co-work, and a solution where you can control co-work through a similar kind of chat. And although it feels kind of secure, etc., the thing is that your context and the thing it does will always be pulled through a public model. So, for instance, if you would ask Claude Cowork to go through your email or sort all of the pictures you took in the last year or so, it will
Yeah.
pull everything through a public model. Whereas with NemoClaw, it does that completely local. So your context and the things it learns stay local as well. To me personally, that's the main benefit. Like I'm not a massive security expert or a someone who's always seeing the risks in everything. But still, this is to me one of the biggest added values of running NemoClaw on the Spark,
Yeah.
and build some of those agentic workflows where, yeah, I don't want a public model to go through all of my pictures,
No,
but this is
no,
really cool stuff.
I agree, and I think this is the essence of the private AI movement, right?
Yeah,
It's still having AI, still having a functional model, yet you don't want to expose some of the stuff that is dear to you. Look, and we don't. Let's not get into security detail too much, but that's the whole idea of AI. Back in the day when we used to deploy ML, it's about understanding patterns that are not obvious, right? And this is the same thing, right? Even though it feels harmless, the fact that you can tie certain things together to get a better view of somebody's life or whatever, I don't wanna do that. So, but getting back to like what's going on with OpenClaw and with NemoClaw and what Claude is trying to do, it shows that the whole value becomes the state again of somebody or a process. Meaning, we're going to capture the the capabilities and the activity for a long, long time in order to learn a certain pattern. Right? That's basically what you see with some stuff like OpenClaw. keep on learning, keep on and adjusting along the way. Now, with OpenClaw, a lot of people say, yeah, this is for people trying to do some sort of automating their life stuff. But if you tie that back to the business world, it's far it's a very valuable process where it basically tracks along with your behavior or with the behavior of the processes and figuring out, okay, these are the trends, these are the things that we're going towards. Let us adjust. That's the value, I think, and I think we're getting into a time where the majority of focus will not be like the large language model itself, but it will be more like agents and keeping state for the duration of that process, and having these long running history patterns, right? And so we're getting back to in a sense to CPU functions and state on disk, and trying to figure out how to capture this in a business way. So yeah, that's where I think this is going.
Perfect segue into today's main topic, and that's, well, I won't call it resource management 2.0, but let's dive into what you've been working on in the last couple of months. So can you kind of briefly explain what it is and why?
Okay, so I've been starting to write about how to actually deploy AI workload on your private AI platform with VCF, with VMware Cloud Foundation. And the way I position it is building it up from the infrastructure up to the workload, but in the same time also providing a memory series to show this is how models are actually behaving from a static perspective and a dynamic perspective, and combining these two. And so what you see right now is a lot of people wanting to deploy large language models on their on-prem environment, but they don't know what to use or how it's going to consume the GPU resources, what to take into consideration in order to build an environment that does not only successfully deploy such a thing, but also provides you the ability to consume your resources as efficiently as possible with the consistent performance, of course. And along the way, I've been explaining every step of the platform or every capability of the platform. I've started with just placement into fractional GPUs, and now I'm in the process of writing the multi-GPU functionality. Now, I can write for a long time. You know this, I write very long articles.
Dude, I'm still waiting for your next book.
Well, this is it, pretty much. But I also create some tools, because sometimes, although the diagrams help, you need to visualize, and you need to not visualize in a generic sense, but why not give you the tools for your environment to analyze and to create some simulations, right? So I'm not tying it directly into your environment, but you can basically select the GPUs that you're using, the profiles that you want to use, and the cluster configuration that you have, like the amount of hosts, the amount of GPUs per host, and that helps a lot. I had a lot of feedback, and a lot of people like it, and they can understand how to build their GPU catalog.
Now, before we dive into the tools, let's start kind of what first of all, what's the problem we're solving here? Because weirdly enough, we've been doing this for many, many, many years. Yeah. It's not that like GPU acceleration or GPU acceleration or acceleration in general within back then vSphere. We've been doing that and we talked about that in the previous episode. We've been doing that for more than a decade. So what is the problem that we're seeing today still when it comes to those kind of newer workloads? And I definitely want to touch upon what GPU fragmentation is. So let's dive into the problem first.
Okay. So let's say you're buying a host with a couple of GPUs, right? And now you have these resources available. It is different than what we've been used to over the last 2 decades. What do I mean by that? Before GPUs, we only had CPU and memory, right? And the platform provided you the capability of over-consolidation. Even if you didn't design for it, even if you said, no, every gigabyte of memory assigned to a virtual machine must be backed by physical memory, right? Or every vCPU core must be backed by a physical core. Even if you did it like that, there was still the ability to rely on it. Meaning, if you put a host into maintenance mode, or if a host fails, there was always the platform capability to say, I know you don't want to over subscribe or over consolidate, but let me do this for you while you're going through solving your problem, right? Maintenance mode or availability. With GPUs, that's not possible. You cannot oversubscribe a GPU, meaning you have to understand where things will fit. Especially if you're using fractional GPUs. Fractional GPU meaning using a part of a GPU via a vGPU profile. So it's a predefined profile of memory and compute. Now that means that you need to figure out, not only on a host basis, but also on a GPU basis, where something can fit. And due to the fact that the platform has some settings, meaning a assignment policy and a distribution mechanism, it can lead to certain fragmentation or siloed capacity. Now, what do I mean by fragmentation? If I say I'm going to use a fractional GPU, and I'm going to use a same size placement policy. That means that if I have a physical GPU, it's empty. It allows to load every GPU profile it's compatible with, meaning typically in an H100 or an A100, you have particular profiles, an 80 gig, a 40 gig, a 20 gig, a 10 gig, an 8 gig, right? And so the moment I select, let's say, a 20 gig profile, and I basically start up a virtual machine with a 20 gig profile, DRS and the whole platform will figure out, hey, I can place it on this particular GPU because it's empty, right? Now, that means that out of, let's use 80 gigs as an example. Out of the 80 gigs, 20 gigs are used by that profile. I still have 60% left. Now, going back to CPU and memory, every time when we looked in at the cluster and we saw this amount of memory is being consumed, this amount of CPUs are consumed. And basically, I mean that the rest of my cluster is still available for consumption. I still can create virtual machines that will basically consume the remaining resources. But that's not necessarily the case with vGPUs, with vGPU profiles, due to the fact there are different layers that create some constraints or some requirements. Meaning, if I have that 20 gigs on that 80 gig and I selected the same size policy, that means that GPU will only accept 20 gig profiles because we locked it in for 20 gigs. Okay, now I'll just fill it up with same size 20 gigs. If I start a virtual machine with 10 gigs, that GPU, although it has 60 gig left, is not compatible with that profile, meaning it won't start on that GPU. Now, if you do that at scale throughout your cluster, maybe due to the fact of your power on operation sequence, there is no GPU that has a locked-in profile of 10 gigs, meaning that virtual machine will fail to power on, even though you might have a terabyte of GPU resources left. It's not compatible with the environment,
which is bad for ROI, and it doesn't scale. So it's
exactly right. And so the thing is, try to explain this. Why can I not power on my virtual machine? And basically, when you click through the infrastructure, you're like, there's enough GPU memory. Why doesn't it work? That's not always obvious.
Yeah, and that's kind of when your cluster is only configured to and your GPUs and the whole shebang for homogeneous profiles. That's a challenge, right? So,
Correct.
and now heterogeneous profile support is being introduced.
Yes. A mixed size has been introduced, I believe, since Ampere. I think so. It's been a while.
Yeah.
But that has some challenges as well. So yes, in essence, you can have that 20 gig locked in on that GPU. But the moment I use mixed size, that 10 gig will actually start up on that GPU. So we solved that problem, right? Great. Problem is there's too much choice. Meaning, if I look at the the profiles that a GPU will provide, like I said, you have 10, 20, 40, 80 gig profiles, but you'll have also 8 gigs and 16 gigs and possibly 4 gigs, if you, depending on what type of profile you're going to use. That means that now, how do they fit on that GPU in the most efficient way? Now, you cannot just randomly place things on a GPU. It has to have some type of structure with everything what we do in the IT world. So what a GPU actually has in mixed mode is placement IDs. So there's a range, let's say 80 gigs. So you have placement ID 0 to 79, right? Making 80 placement IDs. That means that for every profile that the GPU can handle, it has a range of placement IDs. So think about the 8 gig. The 8 gig has a placement ID of 0, 8, and basically you can continue all the way down to until you reach the end, right? Makes sense. Now, if I land the first one, the 20 gigs, on that GPU, and if I then want to place an 8 gig, it won't start behind the 20 gig because that's not a compatible placement starting ID. It has to be a power of 8, right? So that becomes 24, right? So now I have 4 gigs in between. If I don't use a vGPU profile of 4 gigs, it will never fit in between, meaning I just lost that 4 gigs of GPU space.
This is like GPU Tetris.
It is. It's 100% that. And so how can you avoid? Well, can you imagine Tetris, right? And now you have all these angles. But what if you just have square blocks? It will fit better, right? You will basically play until you don't want to play because the system won't beat you anymore. And that's the case with what you need to think about is what perfect profile catalog can I build based on the physical hardware that I have and the workload requirements. And so I don't want to coin it, but instead of slim fitting, go right sizing. What do I mean by slim fitting and right sizing? So let's say I have a small language model that only requires 7 gigs of GPU memory. Now, the first one that is available is 8 gigs, right? Because 7 fits in 8 gig. And that would make sense because you say, hey, if I've got 8 gigs, I basically provide enough resources for the workload, and I can use more, or I can basically place more workloads on that GPU. Yeah, if you have one GPU profile. But if you have other workloads with other profiles, it needs at the cluster layer, it needs to figure out where it can land. And so now the alignment of the placement IDs come into play. So in one of the tools that I created is show me your profile catalog that you want to use, and then provide me with the actual physical hardware that you want to use, and let's do some random placement analysis, and then you can see whether it's siloed or not. Now, so going back from slim fit to right size, in that case, the tool would say instead of using 8 gigs, you should use a 10 gig. because it's compatible with your other choices of 20 gigs and 40 gigs, because it's a power of 10, right? Meaning that the alignment for 20 gig and a 10 gig typically are aligned. Now, again, if I place that 20 gig on at first, and if I load a 10 gig, it will basically place it right after each other, because the placement IDs for 10 are 0 to 9, 10 to 19, 20 to 29, right? So it will fit, meaning that even though you give a particular workload a little bit more headroom, because instead of going with 8, I'm going with 10, I still have the ability to pack more workloads in a more efficient way on my GPU, and it feels counterintuitive. But if you do this if you run more and more analysis, you can actually see throughout the tool that the number of utilization is higher with a more aligned GPU profile catalog.
So so there's a couple of things that really amaze. Well, kind of amazes me. Like, first of all, I never dove into mixed profiles and mixed assignments, and we always kind of been right sizing or architecting platforms with homogeneous workloads, right? So especially from a VDI perspective, you would build your clusters at scale with maybe 1,000 or a couple of thousand desktops, all with the same profile. And in some cases, you were allowed to run mixed profiles, but it was always like, oh, there's a 2 gig profile being assigned or a 4 gig profile, and Windows would dictate what the and the applications obviously what the size would be. But you would do this at scale, whereas architecting for AI workloads is completely different, because you won't be, on average, I guess, assigning 1,000 8 gig profiles, because you won't have those 1,000 8 gig workloads at scale. So there's, I guess, the assessment of what workloads to run on your environment are essential. You need to know the outcome. There's no assuming anymore, because well, we know what the general rule of thumb is when assuming what to design for. So you would ideally use the tool that you built in the planning phase, right?
Yeah, in the planning phase, to say, okay, I've built this infrastructure. Now we're going to expose this to be consumed. What is the right way of it to be consumed? You're not going to review every type of workload that comes in and then assign it a particular profile. You're basically going to create a menu of profiles that are compatible to your environment, and that will lead to a higher utilization, right? That doesn't mean that it's going to actively use it, but if a customer requests, let's say again, 7 gigs, you're going to give it 10, because in the end, at scale, because you cannot control every placement possible, it will provide you with the best placement options for your entire cluster, right? And so I think that's the key, that instead of just stopping to think of, oh, I got a cluster of 4 hosts with 4 GPUs each, I'm done. And now basically I'll do my rest. No, the next thing is you create your automation templates with the right profiles. You're going to create your VM classes with the right profiles. And that's the stuff that you expose to the namespace. That's the stuff that you expose in your automation consumption service, right? That will lead eventually to a better utilization of your cluster, instead of troubleshooting and figuring out why things are not being placed or failed, right? That's the important stuff.
So a couple of questions/assumptions to kind of validate. First of all, I'm assuming that AI Enterprise, from a licensing perspective, is essential to use these types of profiles. Yeah, so the profiles to be used in the mixed mode for AI workloads obviously are compute profiles.
Correct.
Is there a way you can mix MIG with vGPU in the same cluster?
You can. It's on a per GPU basis.
Right.
So I can provide MIG functionality to particular workloads, and that GPU will be in MIG mode. Now, the great thing, I believe it's since vSphere 8 update 2 or update 3, when a GPU is empty, meaning there's no powered on workload anymore, it reverts back to a state, whether it can be time slice or MIG. And so if you basically go and you do the traditional way of creating a new virtual machine and then go to a PCIe device and then select the profiles, you will actually see the entire list of possibilities for that particular physical GPU. So you see the MIG profiles and you see the time slice profiles. At the moment you select a MIG profile and you power on that virtual machine, we will put that GPU card in MIG mode automatically. You don't have to do anything manual anymore. You don't have to reboot it. It is in MIG mode. Now, the moment that virtual machine goes away and no virtual machines are running on the GPU again, and you will then select a time slice mode, it will turn into time slice mode, right? But in essence, you have it's the dynamic element of switching per GPU. So even in a host, you can have some MIG and some in vGPU mode or MIG and pass-through mode or whatever combination you want, right? Whether that's a smart thing, that's a different debate, maybe a different podcast. But yes, overall, everything is possible.
So next to the, how do you call it, by the way? Is it like the GPU fragmentation Tetris assessment solution master 3000, or what do you call it?
It's silo capacity tool, and I'm blanking out on the other one, so I'm going to look for it.
No worries. I'll definitely leave a link to the show notes.
Yeah,
what's really cool, by the way, about this tool, I don't know if it's this one or the other one, but a while ago, one of my colleagues reached out to me. He was working at a large university, and he was running into some mixed configuration issues, didn't know really what the size for, and he reached out to me like, do you have some ideas on how to do this? And I saw you like releasing a blog post, probably literally a day before that or on the same day, but you already released a tool there as well. So I think you guys had some conversations about this.
Yeah, it was interesting because the tool actually helped to solve some of the problems that they were facing. So the two tools that I released as of today is the vGPU silo capacity calculator, basically doing what we just described about, hey, what type of vGPU profile catalog do I need to create, right? And then the other tool that I have is the same size versus mix size placement. And that's the tool that I spoke with your colleague about, is that, hey, if you're designing your platform and you have your GPUs in your host, what type of policies do I need to apply on the vSphere layer in order to get the best utilization? And that's what this tool is all about. So what the tool does, it will say, hey, once you figured out this is my preferred vGPU catalog, meaning I'm going to use 10s and 20 and 40s, or maybe 8, 10, and 20s. Let's do an analysis. If I have this cluster of 4 hosts with 4 GPU each, in mixed size and in same size, and then it will generate a startup pattern based on the fact of, okay, you've got, let's say, 16 H180 gigs, right, or A180 gigs. So that's 1280 gigs of GPU memory. If I have this amount if I have these profiles, I will generate a random order until I basically consume the entire 1280 gigs of resources. And then basically we let it go. And you can actually see the animation of loading, how DRS will load. And of course, it's not 100% accurate because in real life, DRS also takes the CPU and memory load into account, the overall cluster balance, and the requirement of the virtual machine. But that's the analysis that I don't want to give, because I just want to give you a way to understand the impact of the different placement policies, right? And so what you see is you see it load up, and at the end after it runs, and you can use different types of speeds. You can basically say, hey, I just want to see every single one placed and do the analysis itself, all the way up to ludicrous speed where you basically instantly see everything being placed. Now, that provides you with a percentage utilization, meaning on same size, I got on average 60 to 80% utilized, and in mixed size, you typically get between 90 and 100% based again on your catalog that you created. And then you can basically also provide the analysis to say, hey, if I'm using a different type of profile, so you can select and deselect, what will it actually do? And of course, everything is in numbers, so I've also provided Monte Carlo simulation where it just basically does 5 or 10,000 placement scenarios, and so you will get a good feel of what is realistic.
So you mentioned a GPU silo or silo just briefly now. And what do you mean? Like, how do you place a GPU silo in kind of the bigger picture? What is it? And maybe you already kind of explained it, but where does it fit in the whole concept?
Yeah, so a silo is more about I'm still having a lot of capacity available, but not necessarily that's compatible with the required incoming workload. Meaning I've got a GPU locked into 10 gigs. Now my next vGPU profile on this virtual machine is 40 gigs. Still got enough space. I still got enough available capacity, but it's siloed to that 10 gig. It's not available for that 40 gig. Compare that with fragmentation, where fragmentation or stranded capacity. Maybe that's a better word for it. That is the space between the two profiles that cannot be allocated for any type of workload because you don't have a profile that fits inside that area, meaning it's lost forever. With siloed, if another virtual machine comes in with 10 gig, it will be placed on that particular GPU, right? So siloed doesn't mean it's completely unusable. It's not useful for the incoming workload. Stranded is, you just completely wasted a lot of GPU resources, and it won't be used unless virtual machines will be powered down again and a new placement will occur. Yeah.
So another question that kind of popped up is that with the introduction of the Blackwell architecture, NVFP4 was introduced as well.
Yes.
So the precision type is like one of the aspects that is really important when kind of right-sizing your environment, right? So with a different precision, the memory footprint of a model can be completely different. So how do you kind of take that type of sizing into account when architecting such a platform?
Yeah, right now we don't, right? Because it's still in its infancy, in the sense that we still need to see a lot of workloads adapt to that. But it will come, of course. But overall, it's not. It's still going to be the model, the static workload that will define a lot of the requirements for the profile, right? The static profile consumption, meaning I've got this. A great example is GPT OSS 120 billion, right? With the traditional FP16, that would have cost at least 240 gigs of memory. But because it's heavily quantized, it's now fitting 70 gigs, 60, 70 gigs, something like that, right? So it can actually fit inside a single 80 gig GPU. Now, that's just putting the lights on, meaning I just loaded the model. I just need to figure that one out to actually, basically it just needs to be there in order to actually use it. At the moment I start to use it, meaning I'm generating a prompt or an agent is sending some tool output to the large language model. Now we need to have capacity left in order to process the request that's been given to the large language model. That's the dynamic part. And now that's the interesting part, because what type of memory is required for this request? Are there concurrent users doing the same thing? Are they doing the same thing from a request perspective? Are they all asking similar types of questions, like similar complexity types of questions? And of course, what is the position of your completion? It's not, your KV cache and all this stuff. It's not in the same quantized method as the model itself, right? And so your context window becomes, you can use your context window as a worst case scenario calculation, meaning I have 264,000 tokens in a context window. You can calculate how much it is, and then basically you can say, I want to provide 10 concurrent users. Okay, now I can basically multiply it by that, and that's the amount of resources I need. Typically, that doesn't fit on a single GPU, so you need to go into multi-GPU. Now, you cannot assign a GPU for KV cache and a GPU for the model. So it needs to span, and now you're getting into a different world of topology aware, scheduling, topology aware. And so that question that you ask about how do you size on new quantization, it feels promising, but due to the fact that we typically need a lot of memory for the actual use of the thing, makes it extremely complex to build a tool for that. There's a great tool out there, LLM Fit, I believe it's called. Check it out. But overall, it's still a shot in the dark. And with agents now, it's going to be a more interesting one, right? So, yeah.
Yeah, so 2 episodes ago, I had a conversation with Joey Conway from NVIDIA about the newly released Nemotron models. So he was the PM on Nemo 3 Super, which was released recently. And one of the conversations I had with him was around, how do you balance between precision or accuracy and kind of the size of the model, their performance? Like, there's a massive balancing act there. So obviously we can't really look into the future, but like, what do you see when it comes to the future of models? And you mentioned agentic AI or agentic workloads. Like, are we going to see because we can shrink a model to a certain size, but we you can't break iron with your hands. That's a Dutch saying, I guess. But
maybe, but let's educate the world on that.
Yeah, like this is a matter of physics, right? So Jensen Huang, I'm currently reading one of his books, or one of the books that's is written about the stuff that he's been, like, his history and NVIDIA's history, and it's called the NVIDIA way. And the speed of light is one of those phrases that is constantly being used as he kind of motivates the team to exceed the speed of light, and not like in the literal sense, but more as like if there's a challenge you can't kind of face, or you're seeing limits, like be creative and figure out what it is that we can do to actually go beyond what is physically possible. And I think that's the same with how we are looking at models, like the Kimi models that have been released in the last couple of months. They're enormous when it comes to size.
Totally.
I think like a single model will consume somewhere roughly between 600 and 800 gigs of GPU memory. Obviously, that doesn't fit on a Spark or on a single GPU, so you need a completely different infrastructure for that. But are you seeing or are you thinking that models that we're going to see, like in the future, just massive models that are capable of doing all sorts of things? Or are we going to go more towards kind of multimodal environments where we have like smaller models specifically focused on a specific thing, like, computer graphics, computer vision, stuff like that?
Yeah.
And what do you think?
So with everything, and we've been in this industry for more than 2 decades. There's not a black and white world. It's always going to be a hybrid version of something, right? But overall, I think it's going to be more geared towards smaller language models than the massive ones. But if you look at a frontier model, the capability of a frontier model is just insane what it can do today, right? However, for agentic AI, I think a derived model from a frontier model, or let's use GPTOS or the new NemoClaw model. If we can use that and derive the core function and add specific domain specific knowledge or capabilities to that small language model, that can fit the workload better than having this massive model. One thing most people forget is the larger the model, the slower it is, because we have to traverse to a lot of these parameters, these weights. Of course, there's mixes of expert, meaning we're already doing a right size of the workload with the model, meaning I'm not going to use every parameter of my model, but I'm going to use a subset, right? That's what the NemoClaw does even better with a latent mixture of expert as well. Now, in a sense, I think we will see models being more right-sized to the actual task at hand, being specific for that particular agent, and then have a lot of these combined with a larger model that needs to understand the whole concept, right? I'm going to use my large language model as an orchestrator, as a knowledge environment that says, oh, for this particular thing, you need to call that tool. Or for this, you need to do that tool. Or let me combine these answers and let me give you an analysis of that, right? So you need to have that thing. But the actual workers, the actual that crunch the data, that do the thing, those can be very specific small language models. And I think that's where the situation is. Now, there's a different element that comes into play, and that's the durability of the context. Meaning, as long as a particular process is running, we need to make sure that we retain that context. When you look at large language models, chat type of functionality, we will ask you the question, we will get a question back. Maybe we'll ask a question again based on what we got in return. But after that, the session particularly ends, right? Or typically ends, meaning that context is no longer valuable anymore. So basically, we can discard it. With a 12-hour process, an agent, I want to keep the context alive somewhere, that if something fails along the way in this multi-step thing, I don't need to go back and start all over again. First of all, I'm wasting a ton of tokens. Secondly, it's not audible, meaning that, and that's going to be a very important thing in the upcoming years in enterprises, right, or in organizations. Understanding what has been done, understanding which steps are already applied or put into the system, and where the system failed, right? Because then we can basically say, basically just redo these types of steps, right? It's more efficient, and it's more, well, you cannot create weird situations in a stateful system. Now, that means that we need to start to think, where are we going to store that state? That's not going to be the GPU memory, right? A, it's way too expensive, and B, it doesn't make sense, because sometimes it doesn't need to have the history, because we already provided it in the previous step, and it's not necessary for this particular step. So we need to start to think about platforms, particularly storage platforms, that will provide extremely fast capacity as close to the workload as possible. And I think that's where the next step is. So it's a combination where finally, in the AI world, for storage teams, the workload, or sorry, the storage becomes a part of the critical I/O path, because we never had that before. We had an application, typically running a web application, hitting a model API endpoint. So we're getting through the network onto the GPU memory. There was no storage involved at all. right? And now with durable agents, the storage path will become critical again. Yeah.
Yeah, and I think it's always it always depends kind of on the use cases you're running, but like one of those use cases that could heavily depend on this or be positively impacted is like AI assisted coding, right? So one thing we're seeing is that obviously if you have a chatbot and you just use it as your virtual assistant to ask questions and get feedback, and the context window can be relatively small, and the speed of the throughput of the model and the architecture or the infrastructure you're running on, can be okay-ish, especially looking at the chatbots that you use for external use cases, like a chatbot of an airline. Like on an average basis, like if I need to reach out to the airline because I have a question, I can quite often I see just your question has been submitted. Please wait for a minute before we have a call center agent for you available. And quite often your question is just popping up in a queue waiting to be processed by a backend system.
Yeah.
In that case, the throughput and the context window of your environment is probably relatively small, but big enough for you to, it's okay to wait. Whereas with AI assisted coding, the context window needs to be so big. And this is why like a solution like Claude Code is really good, because I heard somewhere stating that the context window is roughly 1,000 tokens. It's like, 1 million tokens. Yeah. It's insanely big.
Yeah, that would make more sense, right?
Yeah. No, sorry. Yeah, I meant 1 million. But have you been playing around, or have you touched upon AI assistant coding already?
Yeah, I use Cursor.
You use Cursor, okay?
Yeah, and it's fantastic. It's absolutely fantastic. And I built the tools with Cursor. And
really?
So I have my own subscription, and I just use it to build tools and do all that stuff. And it's fantastic because you just express what you want instead of just going into the nitty gritty of calls and whatever. Is it lazy? Yes, it's lazy. Is it does it provide function? Yeah, it does provide function, right? So I think it's an accelerator for everybody who wants to get started and who have the right ideas. You still need to have the ideas, and you still need to have the clarity of knowing exactly what you want and what it should do. Right? You cannot basically invent something out of thin air. You need to have a clear mission, right? But it works. And look, let's go back to the VMware space again and think about Power CLI. A lot of people spend a lot of time figuring Power CLI and trying to figure out, okay, if I want to do this in my environment, what type of code do I need to create with Power CLI? And then the people like Luke Dakins and William Lamb and Alan Renouf gave all these great examples, but they were never really the thing that you want, right? There was always this element where they deviated from the use case that you had. So there was always this search for other people trying to solve that particular thing and try to combine these two. With Cursor, it's just, hey, this is what I want. Give me a first draft, and then basically you start to iterate together with Cursor in order, or you can use Claude Code for this as well, to get to the outcome. But because it's trained on so many different examples, it has that functionality, or it can basically derive what you want and can figure out what needs to be done. It's so much faster, and it's in a very elegant way as well. Now the thing is, will I trust it, and will I see it as it's my master and it will do the things? No. When I talk to the engineers internally, the ones that are really successful say, I'm treating it like an intern. I'm telling it what to do. I'm correcting it what to do, but it helps. It does the heavy lifting for me. But the brain capacity, that's still you and me. right? And if you treat it like that, it's a tremendous tool.
Yeah, and this is kind of why I asked the question, because now it circles back to the whole topic of the show, where you, like, architecting your platform for the type of workload you're going to offer and the type of use case you're going to offer is essential, and especially knowing the different types of behaviors of those use cases is essential as well. So,
yeah.
Like, kind of final question before we kind of round up and talk about like the lessons learned. Are you seeing that those use cases are being a bit more, I won't say commoditized, but looking at kind of now we're focusing on assigning or architecting for GPU profiles based on what we know in terms of like, we know that this is the type of the GPU memory that's probably going to be used. This is the type of profile that we're going to assign to that. But like looking at a little bit of a more higher level, that's like from a VCDX perspective, also where we've been focusing on, right? So we know what the business requirements are. We know kind of on a very high level what we're going to do with the platform, and we translate that into architecture and eventually into a platform. So is that kind of something that you're seeing now as well?
Oh, yeah. And you touched on something that I'm working on right now, which I not obviously cannot share in full detail. But if you think what we are doing, right, we're creating a system that has a prediction by the administrator, meaning I think that this capacity will be consumed in these shapes and forms, meaning I'm going to assign a virtual machine 10 gigs, 20 gigs, maybe a multi-GPU of 2 GPUs out of an 8-way system or whatever. But it's always this prediction of the administrator, meaning this shape will somehow satisfy the workload requirements. If you look at what's going on in Kubernetes, there's something called dynamic resource allocation, meaning it does the same thing, topology-aware scheduling, meaning that in a deployment YAML file, I'm going to say, instead of give me 1 GPU or 2 GPUs, I'm going to say I want to have H100s because NV of the quantization of the precision, and I want to have them connected together with NVLink. So because I'm going to span my model. Now that is a workload-derived construct, meaning the workload will define what it wants, and it needs to schedule somewhere, right? That looks like a more aligned functionality to the way we want to consume an infrastructure. But there's tension between those things, because in an ideal world, people will ask what they need. We don't live in an ideal world. Yeah. So there is an administrator that says, I have, or the company has spent a couple of million on this stuff. I want everybody to use this as efficiently as possible. Now, if somebody says, well, let's start with 8 GPUs for my small language model, so it will perform great, I have other workloads that cannot be run because somebody's hogging the system. We've been through this for decades, where we had CPUs, where we had memory, where we have like people with a lot of capacity from a storage perspective, and none of that actually aligned with the workload environment. So the idea is, what is the best one? Is it that from an infrastructure up, a controlled way, from a workload down, a DRA way, or can we combine those two together? And that's where the platforms will go. Where is the hybrid version of that?
Well, that will mean that I'm definitely going to invite you back to talk about those kind of topics whenever they, you are allowed to talk about them. Yes. Now let's dive into the final section of the show, like the lessons learned, and kind of look back at the main key takeaways. So definitely one thing I learned today was that it all circles back to what we've been doing for decades. Think before you act. and start with your business requirements. Start with what is actually the workload that I'm going to use and I'm going to run on the platform, and look at the hardware that you have and the way you would ideally Tetris even the platform for you. So
Yeah,
and,
I agree.
And the tools that you created and the blog posts, like always, like your blog posts are of extreme detail and really helpful, really valuable for not just consultants, not just for admins, but for everyone who wants to really understand how something works. Yeah, these are definitely a go-to source of information.
Thank you.
Next to the tools, like you're making it easier to understand and to know what to size for.
Yeah.
Did I kind of
that's
summarize
my
it?
target. Yeah. No, and that's my target, right? So we live in a world where we are getting to see newer and newer abstractions. Every single month there's a new abstraction going on. But it always boils down understanding the full stack, understanding what you said, the workload requirements, and how does it actually fit. We cannot abstract our way out of this, because we always go back to eventually there's something physical, and the physical has to abide to particular rules. We cannot escape that. So if you are really good at your job, you have to understand the full stack. If you're just winging it, just focus on the latest abstraction and YOLO it. But typically it won't. You cannot YOLO your way. There's no vibe coding for infrastructures, right?
Vibe architecting.
Yeah. No, there isn't. So if you're dealing with a lot of investment, you have to take care of it. Yeah. And that means you have to understand it.
Awesome, man. Well, it has been an honor having you back as a guest in the show. Any kind of final words of wisdom?
No, I think I'm just waiting for the European GTC to be announced. That's going to be interesting.
Yeah, that's definitely going to be interesting. So I'll leave a link to everything we just talked about in the show notes. So the different blog posts. I'll share the DGX Spark blog post as well. I think there's one category, or that it's kind of a multi-post blog. I'll share a link to the tools.
Nice. Thank you,
Frank. Thanks so much for being a guest, and I'm happy to welcome you back whenever you have more news.
Thanks for inviting me back.
Thanks for tuning in to the Private AI Lab. Don't forget to subscribe on Spotify, Apple Podcasts, or YouTube, or the Private AI Lab newsletter on LinkedIn. And visit johan.ml for more insights and experiments. Experiment complete. Until the next one, stay curious.